Okay, attendance sheet is going around. And I believe, correct me if I'm wrong, that this is where we left off last Thursday? All right, so we were looking at some static equilibrium. Today we are moving on with complex numbers, but we're going to be okay with 2 80-minute lectures to get all the way through that. So I do want to spend maybe 20 minutes or so of this lecture making sure we're all on the same page on what we want to be able to do with vectors. Okay, and so the idea was that if I have static equilibrium, that means that when I add up the forces, I need to get 0. Okay, and so that's this equation right here. T1 plus T2 plus W equals 0. These are the two tensions. All right, this is the W. And we talked about last time, step 1 is to write each one of these things down as a vector. All right, and so I believe this is what we came up with. All right, T1, the magnitude. Again, being comfortable with this notation, when we label forces and we just put a value on it like that, what we're talking about is the magnitude of the force. Right? And so T1 is really the hypotenuse here of the triangle that constitutes this vector. Okay? And so if that's true, the x component goes to the left, so it's minus T1 cosine 45i. The y component goes up, so it's plus T1 sine 45j. If I look at T2, right, goes to the right and up, so it's a positive T2 cosine 45i and a positive T2 sine 45j. And then finally the W, right, did not have any I component. It goes straight down, so it's 0. And because it's down, it's minus 9810j. Okay, so this is just recap from last time. Any questions about how we got there before we move forward? Yes?
The weight vector be newtons?
Yeah, and in fact, so if you were going to box these as final answers, okay, in fact, every one of these things would be newtons. So even here, where the values of T1 and T2 are not yet known, these will come out in newtons because this number here is in newtons. Okay, so that's a good point. If this was final answer, we would want to include units and we would want to box it. Other questions? All right, so moving forward, let's go ahead and do this operation, right? Plug it in, see if you can figure out what T1 and T2 are. Okay, and so first term, T1, do we know the cosine of 45? Which is? Root 2 over 2? What takes less ink? 1 over root 2. Okay, so this is 1 over root 2, so is that. All right, so let's plug it in with those numbers. Okay, and so substituting, the first term will be T1. So it's going to be minus T1 divided by root 2. Okay, that's the cosine 45 I, right? Plus, I've got T1 divided by root 2 J. Okay, this is the first vector, T1. I'm going to add to that the vector T2. So I'm going to put a plus here. This is all the same equation. Okay, plus I've got T2 cosine 45. That's 1 over root 2 again. So T2 over root 2 I. Sorry, notation faux pas. Should use little hats. Okay, hats for the unit vector. In fact, let me expand on that a little bit. When we talk about vector notation overall, right, a quantity as a vector in terms of unit vectors I and j, we'll use an arrow over the top here. A lot of textbooks will use a bold print or something instead. The I and the j with the little caret on top, or the little hat, you can write those. Sometimes you'll see them written with an arrow, but the fact that it has a little hat really is a unique symbol that means just the unit vector I, right, or just the unit vector j. So it is a vector, but the idea that it's dimensionless and it has magnitude of 1, that's what the little hat signifies. Okay, so the vector overall, T1, has an arrow on top. The I and j is the little carets, right, or the hats. All right, so T2 over root 2i plus T2 over root 2j. Okay, and then finally, I have to add the w. So plus again, same equation, all right, and I've got 0i minus 9810j, and this equals the right-hand side, which is 0. All right, so the question is now, what do I do with this? Combine like terms. Okay, so the procedure of this, whether or not you know all the numbers here, or whether you have variables in them is beside the point. The procedure is always the same. You group the i's and j's and see where you are. So if I group the i's, for example, I got an I here and here. All right, so I can write this as minus t1 divided by root 2, okay, plus t2 divided by root 2, plus, in this term, 0. That's all multiplied by I. All right, and then I got the j terms. This guy here, t1 over root 2, plus, second term, I got a t2 over root 2. Okay, third term, I got a minus 9810 j equals 0. Right, right-hand side is 0. So at this point, when you solve a vector problem, okay, you should end up, if you're doing static equilibrium, right, with a summation of terms that equals 0, and one term will be something times I, and another term will be something times j. Okay, and so if I add these things up to get 0, then, you know, what does that mean separately about what's in front of the i's and the j's? They got to equal 0, right? So you got to think about the I and j unit vectors just like if you're doing algebra with x's and y's, right? The x can't cross out the y, the I can't cross out the j. If I have independent terms that have to add up to 0, they got to be 0 separately. Okay? And if that's true, then this means that if I look at the I direction, okay, and in fact at this point what you do is essentially you reach the point where you would typically start in a high school physics problem, right, which is just look at it and go, let's look at the x direction, right, and look at it and say, let's look at the y direction. Here, the math tells you that that's what you have to do at this point, right, is the I has to be 0. So in the I direction, this means that minus t1 divided by root 2 plus t2 divided by root 2, okay, plus 0 has to be 0. So that's one equation. Does that tell me anything about T1 and T2? I can multiply the whole thing by root 2, right? And so apparently T1 has to equal T2. Okay, let's call that equation 1. Incidentally, right? Look at the geometry of this. This needs to pass the sanity check. Okay, so I'm holding this up with 2 cables. The whole problem's symmetric. I got 45 there, 45 there. Why would it be anything else than T1 equals T2? Okay, so I don't know what the number is yet, but these guys have to be equal. Okay, and so now, would that be the case if this angle was 30 and that angle was 60? No, right? And so at this point, we would have different numbers, right? I mean, we wouldn't have root 2 in both the terms. We'd have different numbers, and so that would then shift the load, right? And so that math would take care of the physics that you know has to be the case. All right, so great. T1 is T2. Let's look now at the j direction. Okay, and so if I look at the j terms, okay, what does that say? T1 over root 2, right, plus T2 over root 2, minus 9810 equals 0. How many unknowns do I have in that equation? I got 2. Can I use the first equation to get it down to 1? Yeah, because T1 is the same as T2, right? And in fact, even if it wasn't, this might say T1 is root 3 over 2 times T2. I can sub equation 1 into equation 2, right, and see what I get. Okay, and so if I sub equation 1, okay, then essentially where I see a T2, I'm going to go ahead and put a T1. So I'll get T1 over root 2 plus another T1 over root 2. And can I move the 9810 to the other side like that? Okay, and so at this point, can I combine these terms? This is going to be 2 times T1 divided by root 2, right? And that equals 9810. Okay, and so somebody bang that out for me. T1 would be what? Root 2 over 2 times 9810. $69.37. What are the units? Newtons. How much is T2? It's the same number, right? And so T2 is also 69.37 newtons. Okay, so there you go. All right, so the point is, again, I could have taken this problem, and if I had some high school physics and I had a sense of how this worked, right, I could look at this and say, well, you know, the x components have to be the same, okay, and they balance each other out, and then the y components have to add up to give me w, and in one calculator punch, I could probably look at this and go, T1 sine 45, this is still T1, okay, so times 2 equals this, and solve for it, and I would be immediately to this number. Okay, so this is clearly a problem that doesn't need the rigors of this approach. Okay, but the problem now is, what if instead of this geometry, I have a box hanging out here in the middle of the room, and the cables now are going off to the corners somewhere. So now it's three-dimensional. I can't even sit there and draw this thing and get a good sense of what these three-dimensional angles are. Okay, and so if that's the situation I'm in, then if I can write these tensions in terms of vectors and unknowns, then I don't have to sit there trying to figure out three-dimensional geometry on my piece of paper. I can just do the algebra and bam, takes care of itself. Okay, so the vector approach, much, much more powerful. You start getting into, you know, 3 dimensions, also problems when the right-hand side is not 0. Right? When is the right-hand side not 0? Unbalanced forces. Okay, and what do we call that field of study? Dynamics. Okay, when the forces add up and they don't give you 0, now you're in dynamics, not statics anymore, right? And things start accelerating. Acceleration is also a vector, so you got a vector on the other side of the equation. Okay, so just getting familiar with the i's and j's, adding up the vectors, that's the goal of this class. You're going to use this stuff heavily when you move on in statics and dynamics, even initially in physics. Question?
Thus far in 4 weeks, everything we've encountered as far as the x component, y component, x has been associated with cosine and y has been associated with sine. There's a problem in the book.
Yeah. Let's do one right now.
Flips that over.
Let's do one right now. Okay, so that's a great question. Say, is it always that I use a cosine for the x component? Is it sometimes I can use a sine? Okay. In general, if you define the angle theta relative to the x-axis, then by definition the x-coordinate is a cosine theta term. Okay? But as an engineer solving a problem, you can label angles whatever you want to label based on your understanding of the picture. Okay? So the short answer to your question is no. I mean, you don't necessarily need to be using a cosine function to compute the x component. Okay? Not if what you drew on the page happens to have the x component opposite to the angle that you labeled. Okay? And so it's your choice as the engineer how to do it. So let me work an example and see if it makes this more clear. Okay? And this is in fact the last vector problem in the notes from last week. Okay? Which is, you know, what if I have a TV being loaded into a truck? Okay? And how do I balance the forces on that guy? Okay? And so again, in this case, I've got an inclined plane. Okay, and that inclined plane is, say, at 30 degrees. Okay, and this is the ground over here. Okay, and I got the television, you know, that maybe is being wheeled up here. Okay, but here it is, the TV. Okay, and I know I'm in a gravitational field, so G is equal to 9.81 meter per second squared. Okay, and, you know, this thing's going into the back of, you know, the truck over here. Okay, so I got the truck, right, and we got to drive away with the TV. All right, and so the question is, okay, how do you balance the forces here when this thing's on this inclined plane? Okay, and you know, the other great thing about this example is in engineering, you know, you get to model the physics with whatever kind of picture you want to draw. Okay, now in this class, we're going to provide you a picture, right, and we're going to set up the coordinate system for you because what we're trying to test here is how to do the math, right? When you move on one more step, even into physics, right, but then in statics dynamics, you'll have a physical problem. You decide how you're going to set this up. So if I want to know what forces are keeping that TV from sliding back down the incline, okay, then I could draw a free body diagram of the TV. Okay, and again, the free body diagram, is the picture of the object, and then what? What do I put on the object if I got a free body diagram? External forces, okay? And so on an object like this, you tell me, this thing is currently sitting on the incline. It's not sliding up or down, right? It's not accelerating, it's in equilibrium. What types of forces? Now, if you haven't had physics, your answer is probably I don't know. That's okay. Okay, some people in here have had some physics. I got friction. What does friction do? Keeps it from sliding. Okay? So, based on that, if this thing were going to slide, would it slide up the incline or down the incline? It would slide down the incline. So if the friction keeps it from sliding, then that force probably goes what? Up the incline. Okay? So again, these are statics concepts beyond the scope of the class. It's really more for your motivation and entertainment. Okay? And so we will provide you these pictures in here. Okay? So I'm going to have a force up the incline. We'll call that F. That is a friction force. Okay? What else is that? I mean, if this is sitting on the incline, is this the only force acting on it? Gravity. Is gravity a force? Okay, well, that's a different answer. Which one you want to go with, gravity or normal force? Okay. So do I have gravity and do I have weight? What? Say again?
Weight is gravity times mass.
Okay, so gravity is not a force. Gravity is a what physically? It's an acceleration, meter per second squared. Okay, so right there, meter per second squared on g. To make it a force, the force due to gravity is what we call weight. Okay, so you multiply by the mass. Okay, and so did I even say how much this thing weighs? The mass of it is 100 kilograms. Okay, incidentally, looking at the unit, right, tells you whether this is a force or a mass. Kilogram is a unit of mass. If this were going to be a force, and I was in this system of units, then this would say what? Newtons. If I were in English units, it would say pounds. Okay, so you got to look at the problem and say, like, am I being given mass? Am I being given, weight? All right, so clearly I got the weight. So which way does the weight act? Down. Okay, so that'll go through the center of gravity here, and it's got, I got a force down. Okay, and so this is the weight, which is mg. And if the mass is 100 and g is 9.81, then I got 981 newtons like this. Okay, down. All right, and then somebody said, well, I got something else. What'd you call that? A normal force. Okay, so normal force. Which way does a normal force go? Up.
Against gravity.
Against gravity. So in the y direction, straight up? All right, so just to be clear, like this could be x and y, right? So normal force doesn't go y. It goes how? Perpendicular, okay? The word normal in mechanics means perpendicular. Okay, normal, perpendicular to. So I'm going to have a force, okay, which is a force that is acting, right, on the block, but it's acting normal, like that. Okay? Incidentally, why is that? Just because, the prof said I've got a normal force. Look, when two objects are in contact, there's only two ways they can interact. So I'm leaning on the desk, okay? Clearly, I'm putting pressure on the desk with my hand. The desk is putting pressure back on my hand, right? This isn't high school physics. This is like 6th grade, right? Object acted upon, gets a reaction on it, right? Newton's law. So the desk pushes back on the hand, I push on the desk. If I am straight normal to the desk, everything is straight up and down. If I do it at an angle, it's still not moving. Okay, so I'm going to have a combination of two things. Force that's normal and force that opposes sliding. Right? That's the only thing my hand can do. It can push down and it can slide on here. Okay, and so that's the reason why anytime you have objects that are in contact, okay, I can have forces in the plane that oppose sliding This is a two-dimensional problem, so I'm thinking about sliding this way. If it were at a 3D angle, you know, it could be sliding in and out of the board too, right? And I'd have a force opposing that. Okay, but in 2 dimensions, this thing's on an incline. Well, it's pushing on the incline, so the incline pushes back, normal, right? And then it also opposes the sliding, that's the friction. Okay. So again, in this class, I'll say for the 3rd time now, a diagram like this is given to you, right? We're not asking you to interpret the physics. That's the next step down the road. Okay, in here, we give you the picture, and we say, hey, we want to get some equilibrium here. Okay, and so what I really want to do is I want to find the forces, right? The forces F, right, and N, okay, that are acting on the TV. Okay, that's what I want to know. Okay, so here they are. Right, I got a magnitude F, a magnitude N. The directions here are known. Do I know the directions? The angles these forces make here? What do you think? How about, here's the horizontal. Do I know this angle? So this angle is 30 degrees. Okay. How about the normal force? Do I know what angle the normal force makes? So it makes a 90-degree angle with this, right? That's what normal means. It is at a right angle to the bottom. Okay? But what do you think? So which angle would be 60?
The one in the lower right.
The lower right. So let me just be clear here. We can think about this thing making angles in a number of different ways, right? Angle, what? Relative to the vertical. Angle relative to the horizontal this way. You know, one angle I can see right here in the picture, right, is this angle right here. Is that 30? So the angle relative to the vertical is the same for the normal force as the angle the friction force makes relative to the horizontal. Can somebody explain to me why that is? I mean, this is a geometry result. Somebody explain that to me here.
The right triangle, the other angle is 90 minus the one known.
Okay.
The altitude at one angle remains the same, so you still are going to subtract from 90.
Okay.
Subtracting the other angle.
All right, so yeah, I think you're on the right track. Number of ways to look at this, right? You could go right up to the intersection point and take a look at what makes the triangles, but clearly, if I take vertical as one of the legs and horizontal as the other leg, then if this is 30, then this angle I'm labeling here is how much? 60, right? And if I just go straight across here, that one is, and it's a right triangle with this one, so this one has to be 30. Right? So a number of different ways you can draw triangles, but anytime you just rotate things, right, you can identify other angles that will be the same, okay, because it's just rotated. All right, so clearly the normal force now makes an angle 30 degrees as well, okay, here. All right, so here's what I got in a picture. So what I would like to do is equilibrium. Sum of the forces equals 0. So the forces are F, right, plus N plus W, these three forces, right, have to add up to 0. So the procedure that I want to kind of drill into your head in this class is, if I have an equation that says F plus N plus W adds up to 0, then the first thing I should do is what? Yeah, write down each one of these guys, right? Write down F, write down N, write down W, see what I get. Now here's the thing. Got a couple ways I can think about this. I can say, hey, everything's in an XY coordinate system that looks like this. If I do that, one of these vectors is trivial. Which one is that? Trivial means I can write it down by inspection. So wait, it's in the y direction, it's 98.1 j negative, right? But then I got to write n, and I got to write friction, right, in terms of components. Just fine, I can do that. Or I can look at this and say, well, you know, what if I just say that this is x and I say that this is y? I'm the engineer. I get to do what I want. Can't I now write n and f in a trivial way? And now I got one vector that needs components. Okay, and the way I have the picture drawn, you know, it looks to me like I can already see what those components are going to be, right? Isn't it this same triangle here, right, where this top angle is 30 degrees? Okay, so let me maybe make this a little clearer so we can see this. All right, so if I come down here, right, and like this, right, and this is the W, which is 981, right, newtons. That's it, right? This top angle up here is 30 degrees. Okay, so if this is true, okay, let's use that coordinate system, because then F would just be what? Here's the XY system we're going to use, right? Get rid of that one. Okay. F is in which direction? Here's F. Here's my coordinate system. X direction. Do I know the value of F yet? The letter F, is that a component or is that a magnitude? The letter F is the magnitude of the force, right? It's a force of magnitude F in the x direction. How do I write that down? How do I write that down with I's and J's? F is the magnitude. X direction is I. How about the y direction? Plus 0j, right? F is just Fi. This is why I chose the coordinate system that way. It's trivial. I just write it down. How about n? Yeah, it's the y direction, right? So it's 0I plus how much? N. I don't know the answer yet, but that's it, right? Nj. How about W? By the way, the original question was here is, do I always have to use the cosine for the x direction? So maybe you can help me out. I've labeled one angle here as 30 degrees. The x component, the way I've labeled the picture, is the opposite side. Okay? The y component is the adjacent side, only because I chose this angle. I could use this angle, right? This angle down here is how much? 60. So if you want to live in a world where you never write down an x component without using a cosine, you can do that, right? Because I can come here and say, well, I'm going to use this angle, right? And now I'll use a cosine. But the way this problem naturally falls out, the angle in the picture is 30. When I draw the diagram, I get 30 up here in the corner. And so based on that, I'd use 30 to write the vectors. Okay, so if we're going to do that, the x component would be what? Somebody? Go ahead.
The x component would be 0I.
So here's W, right? It's going in the y direction, you know, based on this coordinate system. But I'm over here. So you got to keep in mind, tilt your head sideways. The y direction's here. The x direction's here. So 981 is the hypotenuse, right? That's the value of the W. The opposite side is a sine. So would it not be, right, the x component, is it plus or minus? Down and left, right? Opposite to these two. So I would write this as the weight, which is 981. It's going down times the sine of 30 degrees I. So there's an example of the x component is actually a sine, not a cosine. Okay, and then I would do the y component, which is the magnitude, 981. And in this case, the way I drew it, the y is the adjacent. Okay, and so it would be minus 981 cosine 30 degrees j. Okay, and so if we want, we can put numbers in. Somebody run those numbers for me on a calculator. 981 sine 30 is how much? 490.5? 490.5 I, okay, plus cosine 30? Negative 849.6 J. Okay, now, if I were going to box these at this point, okay, I'd put units on them, right? If this was a final answer, I'd say, hey, that's newtons, and even this one is newtons, okay? So again, the n that I'm putting there is the unit, not the value of the unknown n here. All right, so I wrote down the three vectors. Any questions about how we got the three vectors we just wrote down? Because whether you're doing statics or dynamics or any other mechanics problem, if you don't write the vectors down properly, you're dead from the beginning, right? Are you guys with me on these vectors? Yeah, so if this is 60 degrees, how does that change what we just did here? Okay, this term becomes cosine 60. And how does the cosine 60 compare to the sine of 30? It's the same number, right? So the beauty of it is it's up to you. You look at the picture. If you want to say, like, I'm always just comfortable that x is cosine, then just make sure you label an angle where x is cosine. Okay, and you can always do that. It's up to you. Otherwise, for me, honestly, I set the problem up the way the words and the diagram make sense to me, and whatever the most obvious angle is, I use it, so I don't myself feel compelled to always use the cosine to get the I component. I would do this problem exactly the way I just wrote it here. Are you guys with me? All right, so I want to add up the vectors and get 0, right? F plus n plus w equals 0. You know, there may be people in here now, particularly if you never had high school physics, saying, why does he seriously have to tilt his head and use this different coordinate system? Am I just trying to confuse me here with this, right? Well, as soon as you do this, it becomes kind of obvious. Let's plug in the numbers, okay? F is Fi, right, plus 0j. N is 0I plus nj, okay? W is what we just wrote, minus 490.5 I, right, minus 849.6 j, okay? And this is all supposed to add up and give me 0. So at this point in any vector problem, what do I want to do? Group the terms, right? Like terms. Let's look at the i's. F is in front of an I, right? Plus negative 490.5 times I, right? Plus the j terms, right? What do I have for j? I got the n, right? That one's 0. So I got n minus 849.6 j, right? And that's it, right? Equals 0. So if I look at each term separately, I direction, do I even need to do any math to write down what F is? F is 490.5, right? 490.5 newtons. And of course, it follows that in the j direction, okay, that n would be the other one, right? 849.6. Okay, so if I did not use this coordinate system, okay, and I used 981j for w, and I had f and n written in components, then this would have two terms with an f in it, and this would have two terms with an n in it, right? And they would have sines and cosines of 30 degrees in these terms. And at this point, I would then have to solve two equations, two unknowns, which is not a big deal, but it's more work than if you just set the thing up so that the two unknowns are trivial vectors. Because when you get to the point of looking at the directions, bam, by inspection, you're done. Okay, so you can set the problem up how you want. You don't have to do it that way. It could be done the other way. This is all we want to do with vectors in here, okay? Get you used to the idea of writing them with i's and j's, right? And then being able to add up vectors and get something. Usually you add them up to get 0 in an application like this, but sometimes it's relative velocity, whatever the application is, adding up vectors. Okay, so this makes a good segue to our next topic, which is complex numbers. Okay, and complex numbers, you know, as a math topic, might not seem a lot like vectors. Vectors are forces, motions, things with magnitudes and direction. What does a complex number mean to you guys? If I say we're going to do complex numbers, what does that mean? Say again? A complex number is a number what? Irrational? Yeah, it's not real. It has a part of it that's not real, right? So if it's a number that's just not real, that's called an imaginary number, right? If it's a number that has both real and imaginary parts, which is the most general number that you can have, then that's called a complex number. Okay? And this is where you have to start breaking down your training from high school that says, you know, when you get negative signs under square roots, it means like there's no answer. No. It means that there is an answer, but the answer is a complex answer. Okay? And then it's your job as an engineer to decide, does the fact that the math gives me a complex number mean there's no physical answer, you know, or does it not? And sometimes it means there's no physical answer, and other times it means we're just using complex numbers because the associated math helps us solve physics problems. Okay, and in fact, that is what's done in electric circuits. Okay, it's actually done in mechanics at a very high level. Graduate school, solid mechanics, looking at deformations and things. They use complex numbers there too. Okay, so it's just a tool. Complex numbers are a tool that engineers can use to describe things that have more than one part, much like a vector. Okay, so I want to talk just very basic on the notation of what these are so we all understand the language, and then we're going to dive right into application, which is really all electrical engineering type applications. Okay, so this is complex numbers. All right, so if you have a complex number, it's got two parts. Okay, so complex numbers, we're going to use z, okay, to be what a complex number is. When I write a z in here, I will write it that looks like one of my 2's with a slash through the middle, because my 2's tend to look like this, okay? And so that's what my z looks like, just to be clear. So a complex number z has two parts, okay? It's got both real and imaginary parts. So when I say a part is imaginary, what does that mean to you? I got a square root of -1, okay, in there. So I got something with a square root of -1, and I got something without a square root of -1. So, you know, if I use the following notation, z is equal to the following, say a plus b times I. That's the way you would normally see it like in high school. I over here is the imaginary number, right? Or I can write z is equal to a plus b, and in engineering, not a big fan of I for a complex number because we use I for what else? In circuits, it's current, right? So I got current there. So why don't we use a J instead? Okay, so already, we got I's and J's all over the board here already in vectors. These I's and J's have carets on top. Okay, these are vector I and J's. These I's and J's are just I's and J's. Okay, and when you only see an I or a J that's a lowercase letter in an engineering class, then you are talking about the imaginary number. Okay, and then finally, what we like to do, and you'll see why we do this shortly, make you a little uncomfortable and say we actually don't like this A plus B times J. We actually like it as A plus J times B. Now, mathematically, is there any difference between B times J and J times B?
No.
It's commutative. Okay, we write it this way for a reason. I'll talk more about that as we go. Okay, so all of these guys, these are identical. Okay, so just to be clear, this is just notation. Okay, all of these things are exactly the same. Okay, and so in this picture, I is the same as J. In fact, I'm going to put a triple equal sign, right? A triple equal sign means not just the number has the same value. It means it's the same by definition. Okay? So I is a triple equal to J, and that is a triple equal to the square root of minus 1. Okay? So those things are the imaginary number. Okay? So whenever we use the I or J in these contexts, we mean the imaginary number, and it means just what you guys have already seen before, square root of minus 1. So when I say the complex number has a real part and an imaginary part, what do you think I mean by the imaginary part? Do I mean the I and the J? Is that the imaginary part? These are all the same, right? A plus B times I, A plus B times J, A plus J times B. What's the imaginary part here? Anybody?
The B and the J.
The B and the J. Is the J the imaginary part at all? Okay, again, in complex numbers notation, in fact in math in general, notation is key. You got to be really comfortable with what the notation is, right? So you can move forward. So the real part, which we will write real, R-E, of Z. Okay, that's the real part of Z. This is the letter A. Okay, so this is what we mean by the real part. Okay, the imaginary part, we'll write that as IM of Z. Right, I want the imaginary part of Z. This is just the letter B. Okay, so B is the imaginary part. Okay, and here's a key thing that I want you to understand. Okay, both A and B are real. Okay? So when we talk about the imaginary part, we don't mean the J. We mean the number that multiplies the J. The reason this is a critical point is that when I use complex numbers in engineering, right, if I'm trying to figure out an impedance, right, or a resistance, or a voltage, or a current, and I got a complex number, voltage is not imaginary, right? Current's not imaginary, right? You got current running through you, you're going to know it. You're not imaginary things, right? Okay, so A and B, those numbers are real. Those numbers can be associated with physical quantities and units. Okay? The J, the I, that's the imaginary number. It's a placeholder. Okay? It's a placeholder just like the unit vector I or the unit vector J. Okay? The reason why we end up using these guys, okay, is there is some associated math we'll see very quickly here today that I can do with complex numbers that don't have any meaning with like a vector. Okay? And so I can, do things like, for example, multiply and divide complex numbers. You don't really multiply and divide vectors, right? Not in an algebraic way. Okay, and there's some mathematical richness that you get with a complex number that you don't have with a vector. And that's why electrical engineers have chosen to frame the whole way they talk about alternating currents, alternating voltages, right? Have you heard that expression before? Somebody physically tell me what's the difference between AC and DC? It's not the band. Go ahead.
DC means direct current, AC is alternating current.
Okay, so give me an example, like what would have like a direct current, like in this room right now. Give me an example of something that provides direct current as opposed to alternating current. Battery provides which? Direct current. Okay, battery provides the direct current, the voltage, the current flows. What do we use alternating current here? in the wall. Now, why the heck do you use alternating current? Well, there's a lot of reasons why. You can do a lot of things with the behavior of a circuit. If you alternate the current gets alternated in a sinusoidal fashion, right? Like a sine with a frequency and a phase shift and all the stuff we're going to talk about next week, okay? That being said, anybody know? What is the frequency? What does that even mean?
60 hertz.
60 hertz, okay? So standard, right? A wall outlet, how many volts? 120, 110, you'll hear people use that once in a while. We stick with 120 in here. Okay, on a big major appliance like a dryer, it's how much?
240. 240.
Yeah, so you get about double, right? And so that's the idea. So in here, I got alternating current. It means the current's not flat. It's doing this, right? And so is the voltage in time at a certain frequency. Frequency is 60 hertz. Okay, so this is the physics that we're trying to describe with math in double E. When I have alternating currents and I have associated voltages and impedances, I could have the current doing this and the voltage doing this, and they're not exactly in the same phase, right? And they're shifted around. I got to be able to keep track of that. Complex numbers provides a way to keep track of sinusoidal behavior of things. Okay, and you'll see the connection in a minute why that works. Okay, and so the bottom line is complex numbers for electrical engineers. Raise your hand again if you're being an electrical engineer. Okay, we got quite a few in here. And then everybody else in the room that has to take a circuits class, which is all the mechanicals and the bios and the ISEs and everybody else, computer engineers. Okay, you got to have some level of comfort with manipulating complex numbers because that's how we describe electrical signals in a big way. Okay, and so those are the applications in here. So interestingly, with these definitions, the whole idea of, electrical signals, let me use a mechanical example to think about this. Okay, so let's go back to our favorite one. Okay, what if I think about the position, okay, of the one-link robot? Back to this. All right, so back to the one-link robot that we did with trig, that we did again with a vector, and now I'm claiming I can do this with a complex number. Well, there's a reason we cover this topic right after we're done with trig and vectors, is there's an awful lot of mathematical similarity. All right, instead of the x and y axis, can I instead say that x is actually my real axis? Okay, and over here my y-axis is actually my imaginary axis. Okay, and as soon as I think about that, every point in the complex plane there has an x and y coordinate. X is the real part, right? So letter A. Y is the imaginary part, so letter B. Hey, and so let's think about this. If I have the robot, all right, and it's at a certain point here, okay, and I want to think about the position of the tip, right, over here, okay, it's still just a triangle, right? I got a PX, I got a PY, I got an angle theta right there, and I've got a length of the link. Okay. Now, if P is a complex number, okay, the length of that, okay, often uses a slightly different notation than we would in a vector. Looks like absolute value. The magnitude of P in the world of complex numbers is like an absolute value sign. That's what it looks like. The absolute value, the magnitude of P, that's the length L. Okay? So this is all just notation, right? Because in a vector, I'll normally just put the letter P here, and it's clear that it's the magnitude. We talked about sometimes there'll be a double absolute value sign for a vector. It's just notation. Different textbooks, different profs use different language. Okay, here, magnitude of a complex number with an absolute value sign, that's pretty standard. You see that in math books, you see it in engineering books, left and right. Okay, all right, so how can I write this thing down? In a bunch of different forms. I can write the complex number P, right, is a real part, Px, plus an imaginary part, Py, times J. Okay, this is called the rectangular form. Okay, I can also write this thing down, right, in another form, but let me be clear here on how this relates to the A's and B's, right, is the real part of this, the real part of P, that is the Px. Okay, so from trigonometry, right, how do I get the x component if I know the magnitude and I know the direction? Cosine. So it's what times the cosine? So it's the magnitude p, right, times the cosine of theta. Okay, and of course in this case that's just L cosine theta, right? So this is my real part. Okay, and then finally if I want the imaginary part of p, okay, this is the py. Okay, it's the part that is the y coordinate. Okay, and again, take a look at the triangle. How would I get the py? It's the magnitude p times the sine of theta. Okay, so that is the imaginary part. Okay, so geez, I mean, do we even really need this? I mean, I just did vectors. I got an x and a y. It looks just like the components to me. Okay, that's true. What about the magnitude of p? How would I calculate that? What was that? It's the same thing, right? Isn't this just the square root? Px squared plus py squared. This is the magnitude of the complex number p. What about theta? Can I get theta? I like that, right? Jumped right to the a tan 2. Tan minus 1 will take care of me in 2 of the quadrants. But if I want to be sure I get the right location of this thing, yeah, I need to think in general, a tan 2, py divided by px. Okay, this is, the angle. So geez, this just looks like a review of trig and vectors again, right? I got a hypotenuse, I got x and y components, I got an angle, I got a magnitude. Okay, well, p equals px plus py times j, right? That is the rectangular form. I can also write this thing just like a vector, not, magnitude and direction, but I can write it as p is the magnitude p at an angle theta. Okay, this is the polar form, right, of a complex number. How do I get the magnitude p? Right here, Pythagorean theorem. How do I get the theta? Right there, right, a tan 2. All right, so far I got 2 forms. Okay, and these forms are really no different than what I have with a vector. Okay. The part that makes complex numbers so powerful to solve problems in EE, for alternating currents, for example, okay, is the next part. Okay, and this is what's called the exponential form. Okay, and so here's what this one looks like. Okay, if I start with the rectangular form right here, p equals px plus py times j. Okay. And I substitute in for px and py. What's px? It's right here, right? Magnitude p cosine theta. Right? So I get that plus what about py? Magnitude p sine theta, and don't forget the j, right? The py gets multiplied by j. Can I factor anything out of that? This is the magnitude p multiplied by this quantity, cosine theta plus sine theta j. I'm going to flip the order and call that j sine theta. Okay. I can do that, right? Sine theta times j is the same as j times the sine of theta, commutative. Okay, great. So, boy, here's the thing. This guy right here, cosine theta plus j sine theta, okay, this is e to the j theta. Okay, raise your hand if you've ever seen that before. 1. Okay, not uncommon. This is a new idea. Okay, so e to the j theta is, by definition, cosine theta plus j sine theta. Okay, and this is called, do you know what it's called? Okay, it's called the Euler's formula. Okay, and here's how you spell Euler. It's E-U-L-E-R, Euler's formula. Okay, and so that's it, right? E to the j theta is cosine theta plus j sine theta. Okay, and I'm going to write it here like this, like Euler, the old Houston Oilers. Okay, so it's E-U-L-E-R, pronounced Euler. Okay, and so here's the thing. If cosine theta plus j sine theta, okay, is e to the j theta, then can't I just write the complex number p as the magnitude p e to the j theta? Okay, and this guy is exponential form. Okay, so here's something to think about. Okay. By the way, what's E here? All right, so he's giving me a number for it, right? But the number E is the exponential function to the first power, right? E to the x, right? So we're talking about the exponential function here. Okay, and so the reality is, if you take the exponential function and you make the argument of it, exp of something, okay, on your calculator, right? If the argument of the exponential function is an imaginary number, j times something, then the resulting complex number that gets spit out is this. It's a real number, which is the cosine of that angle, and it's j times the sine of that same angle. Okay? So, in general, if I took out MATLAB and I did exponential exp of, and I put in j times a number, that number should be what? Degrees or radians? Yeah, when in doubt, right, it's radians. Okay, and so, by definition here, this is radians. So we're going to throw you for a loop. When we start using this stuff with e to the j thetas, very common in electrical engineering classrooms to write something like e to the j 59.6 degrees with a degree symbol on it. Okay? Math department would have a heart attack if they saw that. Hey, we do that in engineering all the time. It's convention. Okay, it's notation. Okay, if you go and try and evaluate it and spit out a number in rectangular form, you better have the theta in radians. Okay, you get the wrong answer. So just to be clear, I'll make it clear when we're going to take that liberty and when we're not, and what it means. All right, so I got 3 different ways. I got a way that looks like a vector. Can somebody explain to me what's the difference literally in the notation between the rectangular form of a complex number for this link or a position vector for the link? Which one takes more ink to write down? Position vector takes more ink. Why does it take more ink? Louder?
It has the unit vectors.
Unit vectors, it's got 2 of them. So as a vector, I got an I here with a hat on it, and I got a J here with a hat on it. So I need the letter I and J, and I also need the hats, right? I got more ink. Complex number, the px, there's no placeholder here. It's a real number. The second term is an imaginary number. The coefficient in front of the J, the py is real. It could be a length, right? Number of inches. It could be a resistance, number of ohms. Okay. So, similar. 2 places, I don't have unit vectors. I've got nothing, and I've got a J, the imaginary number. Okay? Over here, right, it's just like magnitude and direction of a vector. Okay? And it's written the same way. I put a number and an angle, and that's it. It's called the polar form. Incidentally, your calculator, any scientific calculator, and a more advanced one like a TI-89, graphing, whatever, you can put it in complex number mode. You might want to look at the PDF online and the instructions of your calculator. You can type something in rectangular form, and you can hit a button, R to P, and then you can go back, P to R, and it'll convert between these two forms automatically. Okay. I say that because you guys are allowed to have whatever technology you want in here. When we ask you to work problems in this class that involve conversion of complex numbers, we're going to want to see the work by hand so we understand you know what you're doing. But it's nice to know that you can check your answer on your calculator. Okay? And so just be familiar, when you take circuits class, you will be using P to R, R to P buttons all over the place. Okay, so you'll get used to that capability. So in here, you could do everything we do in this class without ever using that functionality, but I want you to know that it's there in case you want to play with it. Okay? All right, so I got that. And so here's the thing. Then I got this third form. This. So if I gave you a rectangular form, how would you convert to polar? 2 steps. Say what? Okay, so find a magnitude, I do that how? Pythagorean theorem, right? So to convert from here to there, right? Pythagorean theorem. And to get to theta, a tan 2. So everybody, it's just trigonometry. So I can go from rectangular to polar, everybody can convert. How do I go from polar to exponential? What's the conversion? I give you a complex number in polar, and I say write it in exponential. What do you do?
You're just going to take the magnitude times e to the j times the angle.
Yeah, so there's no conversion,
Yeah.
right? Polar form is shorthand notation for exponential form. It's like, why would I even have 3 forms? Well, if I say multiply some complex numbers together, I got a couple choices. I could try and multiply a binomial. You can do that. It's got 2 terms. I can use a FOIL on it. The algebra is kind of messy. I can keep track of the j's, and I can do that. If I said multiply this, I mean, where's the algebra that taught you how to multiply this angle symbol? This doesn't exist. On the other hand, if I said multiply a couple of these, can I multiply e to the 2x times e to the 3x? How do I do that? What does that equal? What's e to the 2x times e to the 3x? You add the exponents, right? Add the exponents, e to the 5x. I do that. Okay? So the reason we have 3 different forms, okay, and there's really only 2 when you think of conversion. Rectangular, and then think about it as a triangle, and you get polar. Once you have polar, that's just shorthand for this. This allows you to do every type of mathematical operation, right? I can multiply, I can divide, I can do all these other things that I can't really think of how I would do with that. Okay, but there's no conversion. You just write it down. All right, so we're going to need all 3 forms to think about solving problems. Okay, and in fact, what we'll end up really doing is using this form, as I said, as shorthand notation for that. Okay, because the math we're doing is really the math that goes with that, but this is the way we bookkeep the notation. Okay, and so it's neat solving circuits problems. It's like a whole little new piece of algebra, but it's really not complicated. So that's it. I got all these different forms. So, you know, I keep saying this is all about circuits, yet I got robots up here and I got, you know, Z's and A's and B's. Let's do some circuits. Okay, and so what I'm going to do is build up kind of an arsenal of circuit elements so we can start solving problems that have multiple elements. Okay, and we'll get through some of this today, and we'll leave off somewhere in the middle, and then we'll have all the next time to really crank out some good problems. So let me start with an inductor. Okay, so this will be what we call impedance. Impedance of an inductor. Okay, and again, we are talking about here directly out of EE 2010, okay, which is circuits. Circuits 1. Okay, so if you're a biomedical engineer or an industrial and systems, you've got your own circuits system over there. But MEs, double E's, same way, they will all take this. Okay, and again, you'll see this also in the BME version. Well, anybody know what an inductor is? It's a coil. So sometimes in engineering, creativity is not our best suit. Okay, so we think about how will we do a coil, and we're like, well, we'll just draw a coil. Okay? So that's what an inductor looks like. It's a coil. Okay, and in fact, it looks almost like, if you're a mechanical engineer, a mechanical spring that you would draw. Okay, so it's a coil, and you know, what it has is a physical property we call the inductance. Now, if you want to use a letter for inductance, what letter immediately pops to mind? I. Yeah, probably don't want to use I again, right? So there's no I. So it turns out that they use L. Okay, and I'll be honest with you, I don't know the history of that. Okay, L is you know, what's called inductance. Okay, L is the inductance. Okay, so the impedance, what does that word mean? Impedance. Slowing down, right? Like if you want to impede somebody's progress, right? You hear that in football, right? The commentator is going to impede the progress. If you impede somebody's progress, you are slowing them down. Okay, and so what other electrical quantity do we think about as kind of impeding things? Resistance. So here's the thing. What kind of circuit element gives you resistance? A resistor. Okay? Turns out all circuit elements have resistive behavior. Okay? So I want you to think about impedance as kind of generalized resistance. Okay? And this whole idea of like V equals IR, right? Voltage, current, resistance. In general, V equals IZ. Z is my generalized resistance when I have things like inductors, and then we'll talk about capacitors, right? So L is the inductance, the impedance is Z. And the way we keep track of this in an alternating circuit, okay, is we use J times the frequency omega. This is not a W. Okay, this is the Greek letter omega, the one that looks like ohms, but in a lowercase. Okay, it's the frequency, like in a sinusoid, sine omega t, cosine omega t. Okay, that's what that is. J omega times L. Okay, so that's it. By definition, Z is an imaginary number. Okay, J omega L. Okay, and so Z is the impedance. Okay, and just to be clear, what we're talking about, omega is what we call the angular frequency. So it comes from things like sinusoid, sine omega t. So what would be the units on omega if I had a sine omega t? Let me ask you this. What's the sine of 3 meters per second? What's the cosine of 36 ohms? When I take a sine or a cosine of anything, okay, what's the anything? It's an angle. Okay? Based on the physical definition of an angle, what's the units of an angle? Radians is the physical definition of an angle. Okay? So I can't take the sine of 3 feet, right? Or the cosine of 27 kilograms. Whatever's inside the sine or cosine better not have any dimension. Okay? Now, we use another measure of angle that's made up, right, called degrees. And we program calculators to give us the right number when we do the sine of 30 degrees, but the physical quantity in there is pi over 6, right? That's radians. Okay, so that in mind, sine omega t. What's time measured in? Seconds. Sine omega t has to be what? radians, right? And so if t is seconds, then omega has to be, say what? It's radians per second. Now, your comment was inverse seconds. Physically, that's right. I mean, a radian has no dimension. Okay, so in terms of dimension, it's seconds to the -1, but we write it as radians per second because it measures angular movement, right? So radians per second. Okay, so yeah, so this is in radians per second. Okay, great. What else? Dun, dun, dun. L, okay, is the inductance. Okay. By the way, omega, okay, is related to, we're talking about alternating current. You said the alternating current in the wall is what frequency?
60 hertz.
60 what?
Hertz.
Hertz. What the heck is a hertz?
It's a measure of frequency.
It's a measure of frequency. Does anybody know what does a hertz mean, right? We listen to the radio. It's measured in hertz. How many times? It's a counter. How many times per second? When we're talking about sinusoids and rotating things, a time is a cycle, right? So a hertz is a cycle per second. How many radians does it take to do a cycle? 2 pi. So there's a conversion between the hertz and the angular frequency, right? And so omega is this guy. You probably, if you had high school physics, you've seen this one, 2 pi f. Okay, even calculus, right? You might have seen that in there. 2 pi f, where f is the frequency, okay, and that is in hertz, Hz. So physical unit of a hertz, just to be clear, cycle per second. Is a cycle something that has dimension? It's a counter, right? So hertz is physically seconds to the -1, okay, also. Okay, but the idea is that it's a cycle. And so that's why you have the 2 pi factor, right? Omega is 2 pi radians per every cycle. Okay, so 2 pi f. So again, this is all because you got to know the language you're dealing with to solve these problems. All right, so we want to write down the z, given some typical numbers for a real life circuit. Okay, so for example, let's find z. Okay, if. Okay. Oh, I didn't put the units. Inductance. Does anybody know units on inductance? Henrys. Okay. Again, the L, the Henry. Henry was the person. Okay. The L, I'm not sure of the history. Anybody know? Okay, I should look that up. Somebody Google that. All right. So why do we use an L? But this is H is the unit, and that is called a Henry. Henrys. Okay, so inductance is the letter L measured in henries. Omega is angular frequency measured in radians per second. Frequency is the way we normally give information about a circuit. That's measured in hertz. And we got to convert in order to get the omega. So find Z if L is equal to 25 millihenries. What's a millihenry? Milli means, like a millimeter means what? Times 10 to the -3, divide by 1,000. So you might as well just cut to the chase and write it as 0.25H. Okay, like that. So it's 25 millihenries. Okay, and F is equal to 60 hertz, right? So we'll talk about a real life wall outlet. All right, so let's write this down. So Z is equal to J times omega times L. Okay? J omega L. So it just means literally put the numbers in here. So this is J. If F is 60 hertz, then omega would be what? Yeah, so it's going to be 2 pi, right, times the 60 here. So 120 pi, right? So that's the omega, and then I put the number for the L, which is 0.025. So, you know, you could write this in terms of a pi if you want to do that, but somebody give me a decimal number here. 4 significant digits, what's Z? Still got the J in front, right? 9.42 is 5 the 4th significant digit? you round up to 5 or down? All right, so you're saying my notes that has that, the 6 is wrong? It could be. Anybody get a 6? My notes say 9.426. We've been saying that for 9 years. Say what? What'd you get?
9.4247.
Okay, so now we got 5 to 7. Should I split the difference and stick with 6? Seriously, use exact numbers. 2 times the number pi times 60, the pi button on the calculator times 025, and give me the 4th digit. Is the 4th digit a 5, a 6, or a 7?
It's a 4. But when you round it, it's a 5.
So it's a 5. You got 7?
She said 9.4247.
47. Great. How's that? Units on this. Impedance. Generalized resistance, right? Resistance is ohms. Okay? So this is the way you would actually write down the impedance of an inductor circuit element. It's an imaginary number. 9.425 isn't an imaginary quantity. Okay? You could measure it. It's in ohms. All right? So the point is we use the J for this circuit element. Okay? Other circuit elements have other definitions. We will work on those next time. Okay? And then we'll start solving some good problems.